Hi, I'm Rich with Inside HPC. We're here at SC15 in Austin, Texas, and we're here at the HPE booth, and I'm here with Vineeth and Dave Mullally. How are you doing today, guys?
Great, thank you.
Terrific, great to be here.
All right. So let's start with you, Vineeth. What are you guys showing here at your booth?
So really, what we have is we've tailored our sort of story for the HPC developers here, right?
Yeah.
Who are really worried about applications and performance of applications. What's really happened traditionally is that the single-threaded applications have not really been able to take advantage of the multi-core processor-based server platforms. So they've not really been getting the optimized platform, and they've been really leaving money on the table, so to speak. Because when you actually can optimize your applications for parallelism, you can take advantage of these multi-processor server platforms, and you can get sometimes up to 10x, performance boost, maybe sometimes 100x we've seen in some sort of financial services applications, or 3x for chemistry types of simulation kind of examples. So the whole idea here is to be able to modernize these single-threaded applications, to be able to flip them around to do more of multi-threading, right? And multi-processor server platforms. How do you take advantage of that is really what we're trying to help communicate to developers, because we've got a great story from Hewlett Packard Enterprise and Intel to help application developers do exactly that.
Sure, that sounds like that's going to be even more important as Moore's Law kind of slows down. We don't get that free performance boost. You got to take advantage of that parallelism in the hardware, don't you?
Absolutely, Rich. And what's really happening is, there's a fight for performance here, right? We want every single bit of performance we can get. The nice thing is on the hardware side, right, vendors like Intel have been doing that, and HP has been doing that too, to kind of get to more and more teraflops of capacity, for example. But the trick really is about how the application is written and how it can be modified to take advantage of that hardware. Otherwise, you don't get it. So what we're really doing is, our story here for developers and how we want to help them is basically there's 5 things we can do to go help them. First is we can do an entire software modernization plan for these developers, right? Sit down with them, understand the environment, do that for them. We can actually go understand, with the help of software tools, the inner guts of what's happening, what kind of CPU utilization the actual code is doing, characterize that to understand some of that, give them information around that. We can actually provide them some specific, we have subject matter experts in our Center of Excellence to give them specific help with their specific application workloads and ideas and how they can tune it. We can also help developers pre-test their applications on latest hardware platforms, both from HP and from Intel. So we can do that. And finally, we can help them actually modernize their code, right? As I told you, take that from the single-threaded applications to make it more multi-threaded, parallel-based, and take advantage of the multi-core, multi-processor platform environment.
Okay, sounds like a very comprehensive steps and ways to get this done. Dave, can you give us a little bit more on the specifics on Yeah.
Happy to. So can I show you a few things? So let's come over here. And what we're going to do is, these are some examples of improvements that you can get with code modernization that I have up here. We've got, these are just the bare results using BWA, which is a next generation genomic sequencing code, and LAMPS, which is a molecular dynamics application. And we have 2 data sets with LAMPS, and you can see that the improvement that you can get is oftentimes dependent on the data that you actually use. So if we look at this, we like to look at some details, and we use some tools to do this. This is what's happening with the CPU usage as we run the application. This is BWA. We're looking at two sequences against a genomic database, and what you can see here is in blue, that's the application running before modernization. And so we're running about 70% efficiency. We got a lot of big peaks and valleys, so we've got some problems with communication. We've got problems with load balance in general. So after modernization, we get a much more interesting graph, because we've got, in the darker color, we can see that we've got nearly 100% CPU utilization as we run along. And you can see we're actually doing 2 sequences there, and there's a break in between, which is fun. So by improving the CPU utilization, we're getting an improvement in speed of about 32%.
Okay, and that drop-off, that's the code completed then? And
yes, the code completed here for modernized, yeah. And this is where it completed with the original code. So
you get both speed and time.
Speed and time? Yes. Okay. Okay. So is 32%, is that a realistic number to expect on these kinds of things, or is it good use case here?
Oh well, it's a good number, and and it's free. I like free. So for me, free is a big thing. So there are other applications that I've got here. This is lamps, and what's fun here is this is completely different. They've done an excellent job of working on the parallelization here. You've got 100% CPU utilization as you're running. And what you can see though is you start off and again the dark color is with the modernization, and that's about 15% shorter than before modernization. And again we're using 100% beautiful parallelism. If I looked at the code, the profile, I would say can't be helped, but modernization really did. So that's nice. With the same application, this is a different data set here. This is running this is running a liquid crystal calculation, different potential, different path through the code, and instead of just a few percentage difference, we have a 326% difference in speed because of code modernization. So this is really stunningly good. So. And so I've got another thing here because, again, we like cheap and we like free. So we've got an example here using the Xeon Phi. This is using Abacus Standard, which is a structural application. And what you see here is the times in gray, these are relative performance. That is without using the Phi. The light blue times are light blue relative performance is showing you using the performance using 2 Phis. And what you can see here is that we're getting up to a 34% improvement in speed on one of our test cases. And that's great. Now with Abacus Standard, the important feature is to have the number of tokens. The tokens cost more than the machine. So think of the hardware as being free, the software as being the cost. So I care about the number of tokens, so if I look at the number of tokens that I'm using for that, and this is showing the relative performance per token, what I can see here is, again, it's close to free. In this case, we've got an over 30% improvement in speed for a cost of around 3% in terms of tokens. Excellent value. And so we can get that with the Phi, and as again, it's not free, but it's cheap, and I will settle for cheap.
All right. So could we expect, as we move to Knight's Landing, similar kinds of, potential performance gains with that kind of architecture?
Well, with Knight's Landing, I would expect to see better performance gains.
Yeah.
So that will be great. The truth is that the token situation needs to be negotiated.
Okay. Oh, yes, I gotcha.
So
all right. Yeah.
You don't want Similia to go out of business because the Phi is just too fast and too cheap.